So this video is going to be the first installment in a series of videos that explain the solutions to the protein purification practice problems. So let's dive right in. So the first question is asking us to describe what technique we'd select in different scenarios if we wanted to separate proteins with different properties, and to explain the reason for our selection. So the first one is if your proteins differ greatly by size. Now, there are two techniques that we talked about that separate things based on size. So the options are size exclusion chromatography, also known, let me spell it right, also known as gel filtration. And then the other option is dialysis. So what I would choose in this scenario would be the size exclusion chromatography, okay? And the reason for that is I want to separate out two proteins, okay? So both of these separate based on size. But one of them is good for removing small molecules. The other one is good for separating proteins. So dialysis is best for removing very small molecules and doing buffer exchange, okay? Size exclusion chromatography can separate out proteins, and you can actually collect the things that you separate. It can also be used for buffer exchange, okay? But in this case, I would choose size exclusion chromatography, okay? So this one's good for separating proteins. And as we talked about in lab, you can pick your gel filtration resin based on the size of the molecules that you want to separate from one another. All right, so the next question asks us what we would choose if we had two proteins and we knew they had different isoelectric points. So the technique that we talked about in the context of isoelectric points was ion exchange chromatography. Okay, so that's what you would use for this in this case. And the reason, okay, is because it separates molecules on the basis of their charge. And so if two molecules have very different isoelectric points, then at any given pH, they will have very different charges. So ion exchange chromatography, because it separates based on molecular charge. And proteins with different pI values will have different charges. At a given pH. Okay. All right, so the third scenario we're going to look at is what would we choose if we have two proteins that, they're similar in size, maybe similar in isoelectric point, but they have very different functions. So in this case, the technique that we talked about that was somewhat related to protein function was affinity chromatography, and that's the kind that you would choose here. Okay, so affinity chromatography because it separates based on a specific interaction between a small molecule or a small protein that's attached to the column and the protein that you want to purify. So it's related to the function of the protein in that the column has a specific binding partner for your molecule of interest on there. So because affinity chromatography, because it separates molecules based on a specific binding interaction, and that is often related to the molecule's function or like a cofactor that it has. So we're going to say a specific binding interaction that is related to the molecule's function. Okay, so that's the answer to question number 1. All right, question number 2, I'm going to switch to the highlighter, and we're going to highlight the information that we need out of this scenario. So, in this scenario, a scientist has done ion exchange chromatography, and they eluted the protein. They got it to come off the column with 0.4 molar sodium chloride. So that is going to be the concentration of salt in the solution that your protein's in. Fractions containing the desired protein are pooled to yield 5.7 milliliters of sample. So that's how much of that 0.4 molar solution you have. So now the biochemist wants to change the buffer, and it wants to get the buffer into, or get the protein into 50 millimolar tris. So what we want to know is if we do dialysis, where we have our desired buffer, the 50 millimolar tris on the outside, and our original solution on the inside, what will the final concentration of salt be? So we're interested in the concentration of the salt. So the concentration of the buffer that we want to switch into, this right here, this information is not needed. I'm just going to say it's irrelevant to this question, okay? So the other piece of information that we want to know is we've got 2 1-liter changes of buffer. Okay, so let's just sketch out what we're doing in this experiment. All right, so what we have is we have 2 1-liter beakers of buffer, and then we have a dialysis bag, and in the dialysis bag is going to be our solution with the protein that came off of the column. Okay, so what's going to happen, all right, is the dialysis bag here, okay, it's going to have molecules in it that we want to that we want, but it's also got, I'm going to zoom in so you can see the little pink dots. It's also got salt molecules that we want to get rid of. Okay, and so at the outset of our dialysis procedure, okay, we have no salt on the outside, okay, but we have salt on the inside. And so this is going to be after equilibration. We're going to have some salt on the outside, some on the inside, and we're still gonna, but all of our protein molecules will stay in the bag. Okay. So then what we're gonna do is we're gonna take that bag, okay, that has our protein molecules in it, and now it has only a few salt molecules. I'll put more salt molecules in the beginning here. There we go. And we're going to put that in a fresh beaker. Okay. So that goes in here. Actually, I'm going to make use of the copy and paste function here. I'm going to copy it. And there we go. I've put it in the beaker. Okay. And so that's going to have an equilibration process, right? And at the end of this process, so this is after equilibration, what we're going to have is we're going to have a bag that's still going to have all of our protein molecules in it. And what we want to know, okay, is some of those salt molecules left, okay, and we may still have some left in the dialysis bag. But the question really is, what is the final sodium chloride concentration, okay, inside the bag. So the final, what's the final sodium chloride concentration in that bag, okay? So there are two steps where our concentration changes, okay? I'm going to zoom in here again. All right, so this is our initial concentration, right? So our initial concentration we know, okay? And we know that because it's given up here in the problem. So it's 0.4 molar, okay? Now, after I put it in the dialysis and some of those salt molecules move out here, I'm going to have a new salt concentration after step 1. So I'm going to call this, after step 1, okay? So I don't know what that is. And then after step 2, that's going to be my final salt concentration, okay? So now the concentration of the bag that I put in here into step 2 before equilibration is going to be what it was at the end of step 1, okay? Now, if we look at what the molecules did in a step, right? We have a certain number of molecules here. And right now they're just in the volume of the bag. But after equilibration, those salt molecules, the pink ones, are distributed over this entire volume, both the volume of the bag and the volume of the liquid that's in the beaker, that extra 1 liter. Okay, and then same thing with the second step. Those molecules distribute themselves over that whole volume. So what this really is it's really 2 steps where we're essentially diluting the concentration of the salt. Okay, so we're going to treat this like a dilution. Okay, and so we're going to treat the system like 2 successive dilutions. Okay, and after each dilution, we want to know what our C2 is. So remember, our dilutions are C1 V1 equals C2 V2. Okay, and what we want to know is our C2. So C2 is going to be equal to C1 V1 over V2. So the question is, what's our C1 and what's our V1 and what's our V2. Okay, so C1, okay, is the starting concentration of our sodium chloride. Okay, V1, so that's going to be 0.4 molar. Okay, V1 is the volume that is in the bag. Okay, so that's V1 equals 5.7 milliliters. Okay, so 5.7 milliliters. And V2 is the combined volume of both what's in the beaker and what's in the bag. So that's going to be 1 liter, which I'm calling 1,000 milliliters, plus the 5.7 milliliters. Okay. So when we do that calculation, we have 0.4 times 5.7 divided by 1,000, 5.7. And so that comes out to be 0.0023 molar. Okay? That's very tiny concentration. So we've gotten rid of almost, all the salt in the bag just with that one step of dialysis. Okay, so this right here, this number that we calculated, okay, is what the salt concentration is inside the bag, okay, after the first step. Okay, so 0.0023 molar. In millimolar, we would move the decimal point 123. So this is actually 2.3 millimolar if you wanted to write it in millimolar concentration. Okay, so now we just have to do that same calculation for the second step. Okay, and I'm going to do the second step in a different color. I'll do it in light green. Okay, so what we need to know for the second step, okay, is all of the volumes are all going to be the same. We're going to assume that the volume here is 5.7 milliliters and the volume here is 1 liter. Okay, but the concentration of the salt that's in the bag is what the ending concentration was from step 1. So, didn't want to do that. All right, so that's our concentration. That's our C1. So our C1 is, I'm going to write it in millimolars because I'm running out of space. 2.3 millimolar times 5.7 milliliters. And that's all going to be over 1,005.7 milliliters. And that's just, that same number right there, okay? So C2, our final concentration of salt after, 2 steps of dialysis is 2.3 times 5.7 divided by 1,005.7, and that equals 0.013 millimolar. So that is a very, very tiny concentration. All right, so this is going to be the final concentration in the dialysis bag after 2 rounds of dialysis. All right, I'm going to stop this video there, and the next video will give you the explanations of questions 3 and 4.